Hi, everyone, and welcome to the second lecture of Deep Learning Systems, Algorithms, and Implementation. This lecture is going to be a refresher on the basics of machine learning, as well as a walkthrough of softmax regression as an example illustration of all the ingredients of a machine learning algorithm. Now, this lecture is going to be a fairly quick run through of kind of basic machine learning. And the expectation here is that this should be a refresher for you. You should have seen this in some form or another beforehand. Now, if you haven't, if you've seen it in a slightly different form, that's okay. But if this is all brand new information to you, then you probably want to look at kind of a more basic machine learning course before taking this more systems focused and a little bit more advanced course. So let's jump right in talking about two things today. We're going to talk about the basics of machine learning, and then, as I said, using this example of softmax regression or multi-class logistic regression as kind of an illustrative example of these ideas. All right, so first of all, the basics of machine learning. Let's suppose you have the following task, which in fact you will have in your homework. Suppose you want to take images of digits like the one you see here on the right, and write a program that will classify these into one of 10 different categories, the digits 0 through 9. Now, there are a few ways you could do this, but kind of the traditional, I would say, basic programming way to deal with this problem is you sort of think hard for a little while about the nature of digits, right? You think kind of what makes a 0, at least as far as an image is concerned, what makes a 1, etc. And you try to encapsulate this logic in a computer program. This is how we sort of learn to code most things. And when this is something like writing a program to sort a list, this is actually a great way to do things, right? Because we can kind of structure logically the steps of what it takes to sort a list, right? The preconditions, the postconditions of each step, and build the logic that way. But for many tasks, like this image task, for example, this ends up being a pretty hard problem. So I consider myself a reasonable coder, at least normalized to professor level, and also, I guess, excluding some outliers like the other instructor of this course, but normalized across all professors, I'm a pretty good coder. And I would find this task very hard. I don't think I could do it very well. Because again, computers don't see images the way we do. We look at these digits, we immediately see their form, their structure, all this kind of stuff, but computers don't see that. And to build all the logic about how you create what makes a three, and things like this, what are the shapes involved, what pixel values, right? How do you turn a grid of pixel values into an actual classification of a digit? That would be quite hard for me actually to program. And so we need to look, or at least we would like to look, at some other way of solving these kinds of problems. And this is exactly what machine learning gives us. Now, the machine learning approach to this problem, and I should be clear, this is really the supervised machine learning approach to this problem. Supervised learning is the majority of what we'll cover in this class, though we will cover a bit of unsupervised learning later on in the class. But the supervised learning paradigm for this problem is to say, it's hard for us to write a program that can classify those digits. But what's pretty easy for us to do, relatively speaking, is collect a bunch of images of digits along with their known labels or their known target that we want to predict. And then, so we take a collection of these things, which we call our training data, right? And our training data essentially consists of these images. So this thing on the left here is supposed to be an image of a 4, along with its true label 4. And precisely because we are good at this, sort of as humans, we can do a good job with this. And so it's fairly straightforward to do this, to collect a training set like this. Now, what we do then, we take this training data and we feed it into a machine learning algorithm. And from what this algorithm produces then is a model H. It produces some model, which we call H, or hypothesis, or really you can think of this as a mini program. And the way this program works is that if you feed in examples like these images, it will produce the output 4, at least approximately speaking. And so if I feed in examples like we see in the training set, in the training data, this will produce the desired output. Now, of course, what's important about this, if you do this well, it will work not just for examples that were in our training data, but it will also work for pictures in general of digits. Right? And we actually won't talk about sort of the intricacies here of generalization and what makes a good and generalizable function, because what we're going to cover really in the majority of this class and really this course is this box here. And what I want to run through today is basically, what does this box contain? What does it actually have inside of it? And so what this box contains is really three things. And in fact, every machine learning algorithm, more or less, consists of just three different elements. And the three different ingredients are the following. The first is the hypothesis class. So this basically specifies what is the structure of that model H that we actually are going to create with our machine learning algorithm. Now, typically, we say that this model is parameterized by a set of parameters. And what these parameters do is these parameters specify the exact nature of this mapping. They specify sort of how a particular instance of a model will map from its inputs to its outputs. That's the first ingredient of machine learning. The second ingredient is the loss function. And the loss function specifies what makes a good hypothesis. How do we characterize when a hypothesis is performing well on this problem? And the last element of machine learning is an optimization procedure. And this essentially is a way that we optimize over the parameters to find a set of parameters that approximately minimize the sum of losses on our training set. And what's really amazing is that all machine learning algorithms, whether they be deep learning algorithms or simple sort of linear classifiers or gradient boosting or really anything you can propose, all of them, at least supervised learning, though unsupervised learning actually also fits this mold to a certain degree as well. All the algorithms that we have in machine learning fit this basic structure. And so even though there seem to be hundreds, thousands of machine learning algorithms sometimes, it's kind of hard to keep up with just how many there are. One thing that's very helpful is understanding how each of these algorithms fits into this framework, because there aren't really thousands of machine learning algorithms. There's basically one. There's one algorithm that sort of has to just specify these three different components, and then you have your actual sort of instantiation of a machine learning algorithm. All right, so what we're going to do with the rest of this class then is look in some detail at softmax regression, also known, as I mentioned, as multi-class logistic regression, and illustrate these basic components in the context of softmax regression. Now, as I said, again, I'm going to repeat, we're going to go through this quite quickly. And some of these topics, if you have not seen before, this would likely be too fast to go through. But what I want to do is just highlight how softmax regression exemplifies these different elements. And really, you can do the same sort of thing for any algorithm. But we're going to use softmax regression as an example before next class, then moving to basic neural networks. All right, before I actually define these three ingredients, though, for softmax regression, I want to start off with our basic setting. So our setting here that we're talking about is multi-class classification. In particular, a K-class classification setting where I say there's K different classes. And what we have in this setting is we have training data where the inputs to our system are vectors xi. And the notation here, xi being in Rn, means that xi are n-dimensional vectors with real value quantities. So essentially, each xi would look something like this. It would look like a big vector specifying the different elements from xi1 to xin, specifying the different elements of xi. And in the case of, for example, these images of digits you just saw, this could be these elements here would be the different pixel value intensities in the image. The next thing we have is the outputs, or the desired outputs of our algorithm, or they're also called the targets or outputs, or they're called several things like this. And these outputs, yi, are scalar quantities, which really they're because we're talking about a classification challenge, or classification problem, these are discrete values that range from 1 to k, where k is our number of classes. And finally, I here indexes over the examples in our training set. So I ranges from 1 to m and indexes over the different samples or examples in our training set. So this particular notation, I'm going to be consistent with it throughout the course here, and it's important to sort of remember these different things because they will do things like affect the dimensionality of the vectors we care about. But throughout this lecture, and for the majority of this course, n is going to represent the dimensionality of the input data. So this is, how big of a vector is our input. K will be the number of classes, how many outputs we're trying to predict, or how many different classes do the outputs take on. And m is going to be the number of points in our training set, the number of examples we have in our training data. And so, for example, in the case of our MNIST digit classification problem, in that particular example, n is equal to 784. Because our digits in that case are actually represented as grids of 28 by 28 pixels, and each pixel position has a grayscale scalar value, actually ranges from 0 to 1, think of it as. And this is how we represent our image. So there are 784 dimensions of our image. There are 10 classes in our example there because we have 10 different categories we're trying to categorize each digit as, namely the numbers 0 through 9. And finally, in this case, there happen to be 60,000 examples in our training set. So k, n, k, and m take on these values for the example of the MNIST data you will work with. But of course, for other problems, they'll take on different values. All right, now let's talk about the hypothesis function that we think of when we talk about k-dimensional classification. And in particular, we'll also talk about the linear hypothesis class that softmax regression uses. But first, more generally speaking, a hypothesis function, remember this is sort of that first ingredient of our machine learning program, is a function that maps vectors in Rn, those are the inputs, that's the dimensionality of our input, to real valued vectors in Rk. Now this is a bit confusing, or it might seem a bit counterintuitive at first, because we think of hypotheses as generating our outputs, right, which are the numbers 1 through k. But in this case, for various reasons, which we'll cover in a second, we really want hypothesis classes that output a bit more smooth indications of how likely, in some sense, in some very informal sense, we think each output is. And so in the classification setting, we don't actually have outputs that are just the discrete classes. We have the output of a hypothesis function, again, being this k-dimensional vector, where k here is the number of classes. And in particular, in this setting, h sub I, so that would be the ith element of our output, right? So our output, remember, is vector valued. So we would write something like h of x equals a vector, where the first component is h1 of x, all the way down to hk of x. And here, the ith component indicates, in some sense, how likely the class is to be class I. So for example, this component here would give some indication of how likely the class was to be class 1. The next one, class 2, and up down to class k. And I'm using the term sort of likely or belief here in very big quotation marks because these are not yet probabilities or anything like that. We're going to actually talk about sort of a probabilistic interpretation in a moment. But for now, these should just be thought as some indication of the likelihood, or I shouldn't even use that word, the belief that the output is in fact class I for this element hi. Now, in the case of a linear hypothesis class, it is a particular instantiation of this type of this general hypothesis function, where h takes the following form. All right, we say that h sub theta, and we use this notation h sub theta here to denote the fact that theta are our parameters, and h is really even though we think of h as a function of inputs to outputs, h is really also a function of the parameters. It depends on our parameters. So we write h sub theta. And in this case, we're going to write that h sub theta of x is equal to just theta transpose times x, where theta here is a matrix which has n rows and k columns. And just sort of to make sure these sizes make sense, right? Let's make sure that in fact this is a legitimate operation. Theta would be an n by k matrix. So theta transpose, and we just use the transpose actually kind of for reasons of convention. In the one-dimensional case, there's sort of a this makes a bit more sense. So we often use a transpose here. You don't have to use it. In fact, we'll give it up shortly when we talk about the more standard notation for deep learning. But transpose just swaps the rows and columns of a matrix, and so the theta transpose would be a k by n dimensional matrix times well, we think of vectors as being column vectors. This would be an n by 1 dimensional matrix. So their product as desired would be a k by 1 dimensional matrix, really, i.e. a k-dimensional vector. So we are in fact correctly mapping from n-dimensional inputs to k-dimensional outputs. And in fact, in some sense, this is a linear transform between those two dimensions. It's in some sense one of the simplest possible mappings or hypothesis functions you could really have that maps between these two quantities. Okay, so before we move on to this is actually going to be the hypothesis function for softmax regression. But before we move on to the second element, which is the loss function, we want to take a brief detour and talk about matrix batch notation. So it's often more convenient. We sort of, in the previous slide, wrote out the hypothesis as a function of a single example. So applied to this single example in our training set, this is the form of the hypothesis function. But it turns out in many settings to be more convenient to write things not in terms of sort of the application of the hypothesis to a single example, but to many examples at once. And we're going to do this with matrix notation for our operations. Now, it turns out this is actually more than just kind of a mathematical nicety as well. This is also going to be really important when we come to implementing these operations efficiently. Basically, because matrix operations are much more efficient than carrying out many vector operations. And because of this, it winds up, not just on GPUs, but also on CPUs, being incredibly important to implement things in matrix batch form for efficiency of execution. And so this matrix batch notation, I'm sort of harping on it a little bit here because I don't just want to emphasize, it's not just a notational nicety, though it is. Once you get used to it, it's very nice. What it really is it's a way also of carrying out these operations more efficiently in code. And so you want to be familiar not just with how to write these things as a bunch of for loops, but how to write them really as efficient matrix operations. So we're going to define a batch matrix, big X, which is going to be a matrix which is m by n. Remember, m is the number of examples and n is the dimensionality of the input. And what this matrix is this matrix is just a stacking of all the examples in our training set. So in particular, the first element or the first row in this matrix is equal to the first example, x1, but because x are examples, we typically think of vectors as column vectors. To make it a row vector, we have to transpose it. Right? So the first row is this transposed vector. Second row would be the second example, transposed, down to the mth example, transposed. And that's going to be our design matrix containing all the examples in our training set. We're going to do a similar thing for the outputs, the targets. We're going to form a m-dimensional, now it's just a vector, in fact, because each output is scalar valued. They're discrete, but they're still scalar valued between 1 and k. And so we think of a stacking of all these things as just a vector, an m-dimensional vector, which contains as its first element y1, then y2, all the way down to ym. And the nice thing about this notation is that not only can we apply it to the basic matrices x and y, we can also think of the hypothesis function as applying to an entire batch at a time. So for example, we can write h theta of x, overloading notation a little bit, we can write h theta of big X as being equal to the stacking of all the elements h applied to each different element in our training set. So the first row of this quantity here is just equal to the hypothesis applied to the first example. Next row is the second example, all the way down to the mth example. But the really nice thing, of course, is that we can write this in much more efficient, much more kind of compactly than even this. If we look at what this actually is, well, what is this? This is just going to be, well, the first row of this thing, our hypothesis applied to x1 would be, that would be theta transpose x1, but that whole thing transposed. So let's just write that a little bit more briefly as x1, not xi, x1 transpose times theta. Okay. That's the first row of this matrix. And similarly for all the other rows, right? So the second row would be x2 transpose times theta, all the way down to xm transpose times theta. Extend these a bit. Those lines there just mean that sort of I'm emphasizing the fact that it's a row, the whole row, they're not negative signs or anything. But now if we look at this also, we can see, well, this is just kind of the definition of a matrix multiplication. So this thing here just equals, right? The first element is x1 times theta, next is x2 times theta, etc. This is just, of course, equal to our big matrix X times theta. So the nicety of all this is that we can find very efficient ways to write these seemingly complex expressions like our hypothesis applied to every element of our data set. All right, so let's now move to the second element of the softmax regression algorithm, which is a loss function. How are we going to evaluate the quality of our predictions? Well, the most obvious thing we could do in some sense is just this classification. Let's just measure the prediction by whether or not it's correct. This is something called just the error of the classifier, right? It's a very sort of simple, it's the most obvious loss function. And so all it is, so we can measure the sort of the error between our prediction here and the true label via a loss function that we just call sort of either the 0, 1 loss or the error. We're going to call it the error loss, right? And this is sort of a very intuitive loss function, but we can write it formally too, right? We can write it formally as the prediction, the loss that we suffer on the prediction is going to be 0, basically if our prediction is right. But for a classification, remember what it means to be right is that we should be most confident in some sense about the correct class. And again, with our hypothesis function mapping from Rn to Rk, what this means is that this quantity hix, we want, for our prediction to be correct, we want that quantity to be largest at the true class y. And the way we can write this formally is we say this loss is 0 if the argmax, so if the maximum index, the index corresponding to the maximum value of hi is equal to y. Right? And this is very simple. I mean, all this is saying is that if the biggest entry in our prediction is equal to, corresponds to the correct class, we suffer loss 0, otherwise we suffer loss 1. And really, actually, this is very often how we assess the quality of classifiers. It almost goes without saying. It's almost so obvious that we don't even bother saying this in some sense. But this is very frequently how we actually assess the quality of classifiers. Whenever you report error of your classifier or accuracy of your classifier, this is how we do it. Of course, accuracy being 1 minus the error, right? What the average error of a classifier is just the average loss, this loss averaged over the whole data set. So this is a very intuitive loss function to use for classification. The problem is this loss function is very bad for optimization. It's not very easy to find a set of parameters that minimize this error loss. It actually winds up being, for even a linear classifier, an NP-hard problem to find a classifier that achieves the minimum number of errors. But maybe more fundamentally, another sort of very annoying thing about this loss is that it doesn't provide any information. It's not actually what we call differentiable. And what this means is that if we vary our hypothesis a little bit, this loss typically won't change, right? It won't change locally around our current set of parameters because you're probably not right on like a switching point where one thing switches from one to the other. And even if you are in a switching point, that's sort of a point of also a non-differentiable point because it sort of switches back and forth immediately between 0 or 1 loss. And this is very bad for actually optimizing parameters because, as we'll see in a second, in really not all machine learning, but in probably all of deep learning, the most common way of optimizing parameters, of finding parameters that are good, are via gradient-based methods, via derivative-based methods. And so this loss function is very bad for actually optimizing over parameters, even though it might be good for quantifying the performance of classifiers. And so what this leads us to is a different loss function that we're going to use for softmax regression, called either the softmax or the cross-entropy loss. This term cross-entropy loss has become kind of the standard in most machine learning these days. And so we will define it, in fact, as the cross-entropy loss. And in order to define this loss, we're going to convert between our hypothesis output, right? This is these in some sense, these predictions that correspond to some kind of vague notion of belief. We want to convert that into something that looks more like a normal probability. All right, so we want to take our hypothesis function, these real value quantities, and we want to convert that into a probability. And the way we're going to do this is we're going to define the probability that the label is equal to I. And we're also going to call this term sometimes just Zi, just for convenience here. Now, what do you need from a probability? Well, a probability has to be positive, and it has to sum to 1, right? And our hypothesis output, Hi, that is not positive. It can be -2, and doesn't have to sum to 1. So how do we make it sum to 1 and be positive? Well, the first thing we can do is we can just take our hypothesis, Hi, right? Take this term Hi, and just exponentiate it, right? So now that will make it positive. Okay, so we just exponentiate any number, positive or negative, the result will always be positive. But they won't always sum to 1, so that sort of solves the first problem, probabilities have to be positive, but that doesn't solve the second problem, where probabilities have to sum to 1. So the thing we can do next is just normalize this quantity by the sum of all the outputs, right? So we're going to take our hypothesis at index I, exponentiate it, and then we're going to normalize it by the sum over all our exponentiated hypotheses. And now this quantity is, in fact, at least obeys the basic principles of a probability. It is positive, and the sum over all the probabilities of all the labels will always equal 1. Another way of writing this is to say, in vector form, is to say that Z, the vector of all the probabilities, is the normalized function, that just means we divide by their sum, applied to the exponential of the hypothesis function. One thing that will come up a lot is that whenever we take kind of a scalar function here, like the exponential, and apply it to a vector, all this term here means, it just means the exponential applied to each element in that vector h of x, right? And so we're going to frequently apply kind of or scalar functions to this, and you kind of have to infer what we mean just by the context here. So normalize actually is a little bit more complex because it looks at the entire vector, but all this normalize function does is for a vector, it makes the vector normalized to sum to 1. All right, so that's how we're going to map. And you may be familiar with this operator. This is also called a softmax operator. It's sort of a standard way of mapping between arbitrary real value components and the output of or in a probability distribution. Now, you may, if looking forward a little bit here, if you are familiar with neural networks, you may have seen things like this where people often take this operation, which they also call, so this is also called a softmax operation, I should say. This is also equivalent to the softmax called of just h of x. So softmax is just the combination of the exponential and then normalizing it. You may see sometimes in neural networks, people define the output of a network to be the softmax applied to something before that. But that actually, for various reasons, that's actually not the right way of doing things, in my opinion. The output, and even in a setting like this, right, the output of a linear classifier is just the linear function, not the softmax applied to the linear function. The softmax and these sort of things, at least at the final level, final sort of loss function layer, becomes an operation that sort of is embedded in the loss itself, not an operation you apply to the network. I'll come back to that in a second, though. All right, so now that we have a probability here, that we sort of mapped from our arbitrary hypothesis output to a probability, we need some way of quantifying whether our probabilities are good or not, whether our vector of probabilities is a good set of predictions or not. And this is now fairly obvious what we might do. A good measure of how good our prediction is the probability of the true class high, right? So what's the probability of under this notation, what's the probability of the label being the true target y? And so we want to make that probability as large as possible. But for sort of reasons of convention, we typically think of loss functions as being things that we minimize. So we want to make something small, some like error small, right? So we could minimize then, I guess, the negative probability. But minimizing probability is actually, for various reasons, is a bit not very well numerically conditioned. So what we typically do is we take the log of this thing. And this is a very common thing. This is called the negative log loss, or it's a sort of very common way of deriving loss functions, where we define our loss function, and we in fact define the cross entropy loss function as just the negative log probability of the label being the true class under this distribution here. And we can write that out a bit more explicitly. We can just sort of write this out a little bit more concretely here as also equal to, well, let's just sort of take the log of this thing. So we have the negative log of the numerator first, which is the exponentials. The log and the exponential cancel. And we just have negative hy of x. So negative the yth component. Remember, y here is a discrete value between 1 and k. So we take the yth component of our output. Then minus the log of the denominator, but then we also subtract off, because we're taking the log of the denominator, we subtract that off, so we're in fact adding the log of the sum from j equals 1 to k of the exponential of hjx. Right? And that is called the cross-entropy loss, or sometimes the softmax loss, or just the multi-class logistic loss, sometimes it's called, but these are all really the same thing. And the name cross-entropy loss is the most common these days in machine learning. And that's how we define the loss function we're going to use in softmax regression. Now, as I said before, the right way to think about this is as this loss function applied to a linear hypothesis class, not sort of this negative log being the loss, or this negative log here being the loss, applied to some softmax of this thing. And there are subtle reasons for that. For example, if you look at the convexity properties of this thing, this problem ends up being, well, for softmax regression, will end up being a convex problem. That's much easier to see here. You also typically, unless you really have to, don't want to actually form a softmax operation, because If the number becomes numerically 0 and you're taking the log of a 0, then things can blow up. So it's much better to think of the output of a hypothesis class being a linear function. In this case, these things are, for those that have heard this term before, these are also called, the output of a hypothesis class will also be called the logits sometimes, and then fed, when they are then fed into a this cross entropy loss. But this is the right way of doing things, both I think conceptually, but also numerically. It ends up being much nicer to sort of, you don't want to actually compute this softmax operation here explicitly. You want to compute this loss function applied to a linear hypothesis class. All right, so now with that, let's talk about the final ingredient of softmax regression, which is actually going to take the most time to cover, because we have to sort of discuss a little bit about how you optimize these things. But before we do so, again, this is going to be the third and final ingredient of softmax regression, which is going to be the optimization problem. How do we find good values for those parameters theta? But before I do that, I sort of want to specify or just mention the fact that what the third ingredient of our machine learning algorithm really is doing is solving the following optimization problem. We are minimizing over theta. So what this notation means, so this notation here is notation for an optimization problem. That means we're searching over all possible values, or at least trying to search over all possible values, to find some value of theta that minimizes the quantity here on the right. And this quantity is just going to be the sum from I equals 1 to m, I guess really the average, right? So the average from I equals 1 to m of our loss function, so our loss here, applied between our prediction on the ith output and the actual ith output. Right, so so I want to take a little bit of time to emphasize this problem here, because this problem, kind of stated as such, I kind of think of this as the core machine learning optimization problem that describes all machine learning algorithms. Every machine learning algorithm, in one way or another, is trying to find a set of parameters that minimize the sum of, or the average loss between some predictions and the true labels on the training set. And in fact, this formulation here really includes, therefore, all the aspects of a machine learning algorithm, right? It includes the hypothesis function, it includes the loss function, and it includes the optimization problem. So really this problem, maybe with some slight changes like adding regularization, but we typically don't even do that in deep learning that much. But this problem really is the core machine learning problem. And every algorithm, every machine learning algorithm that there is, in one way or another, solves a problem like this. At least every supervised algorithm, probably every unsupervised algorithm too, and arguably every reinforcement learning algorithm or not. That one's a little trickier, but certainly every supervised learning algorithm is just a different take on solving this problem. And so we can even look sort of concretely, what does that look like then for something like softmax regression? Well, in sort of the simplest way of writing it, it's just pretty similar, right? We're minimizing over theta, that part's the same. We're trying to find good values of theta. That minimize, all we're gonna do here is plug in the specifics of the softmax regression. So we're minimizing the cross entropy loss. And our hypothesis class happens to be a linear one. So it's going to be theta transpose times xi and yi. And this is the optimization problem we want to solve for softmax regression. Now, of course, the question is, well, how do we actually find that? How do we find the value of theta that minimizes this, or at least the value of theta that is this sort of matrix of parameters, remember? The way we define our hypothesis function. How do we find the values that provide a good mapping between inputs and outputs? And so the way we're going to do this is via a technique called gradient descent. But to cover gradient descent, I first want to go a little bit of a digression about a quantity called the gradient. And so let's suppose that we have a matrix input scalar output function. All right, so a mapping from in this case, I'll just use our actual mapping, theta, which is n by k vector, to a real valued vector. And actually going back to the previous slide for a second, the thing I want to emphasize is that this whole quantity here, in fact, right, the thing that we're trying to minimize, for the purposes of minimization, we can think of this as just a function of theta, right? So the quantity that we're going to be taking the gradient of later on is exactly going to be this optimization objective. But for such a function, so for some function f theta, how do we actually start to minimize that function over theta? Well, one sort of very nice thing you can do is use this quantity called the gradient. And what the gradient is a vector, sorry, a matrix of partial derivatives of this function. And in particular, if theta itself, or the input to the function, is n by k dimensional, then importantly here, the gradient, which we write as this little upside down triangle, the gradient with respect to theta of f of theta, that's how we sort of write this. This is also going to be an n by k matrix. And it's going to just be a matrix of all partial derivatives of this function. So the first element would just be the partial derivative of f of theta with respect to theta 1, 1. Going to the last element in the first row would be the partial derivative of f of theta with respect to theta 1, k. Down here, partial derivative with respect to f theta, theta n1, and finally all the way down to the partial derivative of f of theta with respect to theta n k. And these partial derivative signs, what the partial derivative just means is that for the purposes of that derivative, for the purposes, say, of this derivative here, you are treating every other element of theta besides theta 1, 1 as if it were a constant. So every other element that you differentiate, you would just treat as if it were a constant term that were not a function of theta 1, 1. That's what the partial derivative here means. Okay, so this is the definition of the gradient. Okay? And now one thing I really should mention here is that this notation here is admittedly really bad, but it's the thing people use, and so we're gonna have to get used to it to a certain extent. And the reason why it's so bad is that this first usage of theta here, this is actually saying what parameter we're differentiating with respect to. So if f has one argument, you actually don't even need that subscript. You're always taking the gradient of its argument. But as we'll see later, if a function has a lot of arguments, you want some way of specifying which argument you're differentiating with respect to. And so this is sort of what this subscript is saying here, right? It's just saying which argument we're differentiating with respect to. This argument here is an actual value of theta that we're differentiating at. It's the point that we're differentiating at. And so it causes quite a bit of confusion, but the reality is you have to just get used to this. So sorry, the notation is bad. We use a lot of bad notation in machine learning, but I'm intentionally including bad notation rather than introducing better notation. Some people use an index here. They'll use like 1 or 0 or things like that. And that's objectively better notation, but it's not common. So I'm going to use the common but bad notation, and you'll have to just kind of, unfortunately, get a bit used to it. Now, the nice thing about this gradient is what this gradient does is it points. Remember from sort of 1D calculus, right? The gradient or the derivative of a function was equal to the slope of that function. Well, that same intuition holds in higher dimensions too. And so if we have some function, so this function here is like a function where, this would be like the minimum, and these would be like, points of the function getting bigger and bigger. What the gradient does, remember, the gradient is sort of itself a matrix, or for a vector case, if the input function was vector value, it would be a vector. It points in the direction of greatest increase of f, at least locally. So if we're right here, if this is theta, the theta value we're evaluating the gradient at, then the gradient would point in the direction of maximal increase. And that's a very, very powerful notion, right? we don't need to somehow search all possible values of f for the one that actually causes it to increase the most. With a little bit of calculus, you at least in a local sense have the direction, already immediately have the direction in this parameter space that increases the function the most. And that's sort of amazing. You can get it basically, and as we'll see, there typically exist ways of computing gradients very efficiently. This is what the whole lectures of automatic differentiation will cover, but we can compute it very efficiently, and in doing so, we can really easily figure out how to change or how to optimize our parameters theta. So how do we do that? Well, this leads us very immediately to the kind of the core algorithm, I would argue, of almost all machine learning, right? So how do we then use this fact to optimize our function? Well, if the gradient points in the direction of maximal increase, then if we want to minimize our function, which is again the convention for sort of minimizing losses, what we can do is we can set theta to be equal to theta minus some multiple of its gradient. So here alpha is what's called a step size or a learning rate. It's just some small positive quantity. So we subtract off some small positive multiple of the gradient. And it should make sense that these are all the correct size here, right? Because theta here in our case is n by k, and the gradient's also n by k. Multiplied by scalar just scales the whole thing. And so this is sort of a valid update we can do. All the sizes check out. And the key idea, though, is because the gradient points in the direction of greatest increase, if we want to minimize the function, then subtracting off a small amount of the gradient causes that function to decrease. Now, and this, actually, before I go into the details of this, I should just take a moment to say that, to sort of appreciate the power of this approach. So it is not an exaggeration to say that this basic idea of gradient descent powers all deep learning. Maybe not, there's probably a few gradient-free approaches that people occasionally use, but 99% of all deep learning, and because deep learning is so prevalent here, you have 99% of all, 90% say of all AI that you see, right? So those images of dogs, dog professors you saw last lecture, these large language models, these AlphaFold, they're all basically built using this one line of math. That for some reason actually is also still not often taught in like their first undergraduate course, which I think is crazy. This is such a fundamental algorithm that it is really hard to overstate just how impactful gradient descent has been on really the field of machine learning, but arguably even the world as a whole right now, right? So it's really an amazing algorithm that is foundational at this point to all deep learning. And of course, when I say gradient descent, I mean gradient descent and its variance, really any gradient-based optimization technique, but it is still amazing how prevalent these things really are. Now, the one sort of big question you have here, you may have looking at this, and you will continue to have it even as you get very experienced with machine learning probably, is what value we should pick for this alpha here. How big of a step do we take? And it turns out, we'll actually cover this a lot in the course, but the choice of alpha here really very greatly affects kind of the behavior of this method. So if you take a small alpha, so I'm showing here just another simple function. So this is these blue lines here correspond to level sets of the function. I'm just kind of bold out like this. And if you take small gradient steps, you sort of make small, slow progress, right? You sort of go here, and you kind of make small, steady progress toward the optimum. If you take bigger steps, you sort of make pretty good, fast, rapid progress, much more rapid progress toward the optimum. Or if you take too large step, you start kind of bouncing around and not being optimal anymore. And in fact, if we take a much bigger a step, we can take such a big step that we actually overshoot and increase our function each time and kind of diverge off to infinity. Actually, it wouldn't quite follow that path. It would bounce around a bit differently. I guess it would go like here and here, but whatever. Wouldn't do that last one, but here, and it would sort of shoot around this thing somehow. wouldn't do that. I have a hard time drawing the paths, but basically you will start to diverge and not converge to anything. So the choice of step size here is really, really important when it comes to choosing how we optimize this function. And in fact, as a quick preview for a few lectures from now, if you've heard about optimization methods like ADAM or gradient descent with momentum, things like this, what those essentially are those are ways to try to accelerate this process without having to worry quite as much about step size. That is a huge simplification, I know, but basically a lot of slightly more advanced optimization methods are just ways of trying to optimize these things with a little bit less effort in picking step sizes. All right, and now finally, what I'll say is even the last algorithm we described is not quite the thing that we really do in deep learning, because if we look at our loss function, what is the thing we're trying to optimize? Again, we're trying to minimize over theta. This is now, again, for sort of general machine learning, not just softmax regression. The average of the loss applied between the hypothesis, sorry, not x, h, xi, h of xi, and yi. And if we were to take the gradient of this whole thing, well, the gradient of this whole thing would just be equal to the sum of all the gradients of it. So the gradient of this whole thing would be equal to the sum from I equals 1 to m of the gradient with respect to theta of that thing. And the problem there is that if I get more data, sorry, this to be clear, this is the sum from 1 to m. Very clearly. If I get more and more data, to apply gradient descent to my kind of core optimization procedure, I would have to do more and more work for each gradient step, which is really kind of wasteful. It's sort of bizarre to think that if, in the limit of having infinite data, we will actually make no progress because we will just forever be computing our gradient, which doesn't seem to be the right thing, right? And there's also other issues too, right? Like if in deep learning in particular, if you try to compute the gradient over all your data, you will run out of memory. You can't fit all your data in memory, let alone the terms you need to compute the gradients in memory. And so you'll actually not be able to do this. So what deep learning really does is not run classical gradient descent, but it runs a variant called stochastic gradient descent, or SGD. Now, SGD kind of in theory can be formulated as kind of this stochastic minimization procedure where you have you're sort of sampling random variables which are an expectation, have the expectation of the true gradient, but have some variance to them. That's sort of a mathematical interpretation of SGD. What SGD in practice means is that you just split up your data set into what we call mini batches. So these basically what these are subsets of your data of size B. So big B here is what we call the batch size or the mini batch size. And what we do in stochastic gradient descent is we first sample a mini batch of data. So we sample B examples, or maybe more than even sampling them, what we really typically do is divide the whole data set up into however many we need to have each one be size B, and then just cycle over all these subsets of size B. So we take this up to the size B, where we have both I guess we should emphasize, we have both the input, now matrix of the stacked form of all these B examples, and the corresponding outputs. And we update the parameters by taking a gradient step as if our loss was just those B examples. And so the way to think about this is that each step we take here is sort of a rough approximation to our true gradient, but one that we can take much more quickly. And actually, there are even sometimes some advantage of this in the case of deep learning in particular, because we often, can having a little bit of noise actually can be helpful in some cases too. So it's sort of a noisy approximation of the thing we think we would ideally like to optimize, but it's one that we can optimize much, much quicker. So basically, rather than summing over, just to emphasize this in our equation here, rather than summing over all m, we could just sum over all b, and that's much faster to compute, right? Because there are only b of them, which is, hundreds, say, instead of millions, potentially, of examples. And now I can sort of more formally say that, in fact, this is the algorithm that drives all those advances you've seen in deep learning over recent years. This and very minor variants are how, for the most part, we train every single deep learning algorithm. Though we will talk later about how we actually, some of the more kind of common methods like momentum or like atom and things like this. All right, so that's it. This is the optimization procedure. It's the third ingredient of our softmax regression algorithm. But to finalize it, we have one last step, which is how do we actually compute the gradient of our objective, of the sum of losses with respect to our parameters theta? In other words, how do we compute the gradient with respect to theta of the thing we want to optimize, which is the sum of a bunch of these terms, but we can take if we can compute the gradient of one such term, we can just sum them all together to get the gradient of our entire objective. So how do we do this? Well, it turns out it's actually not that hard, but it's not that easy either. And in fact, when I learned machine learning, this is what you did, right? You devise a new objective and you go through by hand and derive all the gradients. We live in better times now. And the reality is, most of the time when you develop models, you will not have to do this. In fact, the whole point of automatic differentiation, which is what we're going to cover in a few lectures, is an algorithmic way of defining just what the hypothesis and loss function look like, and then basically letting the program automatically compute gradients for us. Automatic differentiation is just a programmatic way to create gradients. But for this lecture, and for the next lecture actually, I'm gonna show you what you've maybe seen before. We're gonna pretend we don't know that yet. I'm gonna show you kind of what you may have seen before if you've taken a machine learning course. Because to write an automatic differentiation tool, you will have to at least take some gradients. So you will have to compute some gradients here, and I'm going to take you through kind of, I guess, how we used to do machine learning, which is manually deriving the gradients for all these things. And yes, we really did do this back in the day, the dark ages. Even though automatic differentiation goes back to the 70s, it really did not take hold until deep learning really took off. This was sort of the genesis of these tools being really widely popular. All right, so how do we compute this gradient? Well, it turns out it's actually not that easy, but we can break it down step by step. It's not that hard either. So let's first do the following. So it's computing this whole thing, actually, it is a bit tricky. Doing it correctly is actually very cumbersome, if I'm honest. But let's start off, and we're going to do it kind of incorrectly in a moment. But let's start off with doing a simpler problem. This term here is a matrix. This here terms of vector. It gets a bit, they're sort of, you have to apply the chain rule, that kind of stuff. Let's take a simpler problem, and first just think about treating h not as the hypothesis class, but just as an arbitrary vector. It's actually going to be one step of our derivation, and let's see if we can differentiate compute just the gradient of our cross entropy loss, treating its argument h as a vector. So basically we want to compute this thing here. But remember, the elements of the gradient are just equal to the partial derivatives, this thing here. So I'm just going to first, to compute my gradient, I'm going to first compute what the partial derivatives are. So let's just do that. So this is going to be equal to the partial derivative with respect to hi of, well, what? Well, I'm just going to write our loss function again. So this would be negative hy, because you can go back a few slides, but just trust me, I'm just going to be rewriting now what the cross entropy loss actually is, plus the log sum from I equals 1, or I'll actually use j, because I use I to index over examples. So j equals 1 to m to k of the exponential of hj. I'm just writing the definition of the cross-entropy loss using h's now as arbitrary vectors. Okay, so what is this? Well, this first term, let's just do this. What's this derivative of this first term here? Well, that will be 0 unless I equals y. Otherwise, it'll be 1, or otherwise it'll be -1, actually, right? So if y equals I, this derivative of this term is -1. Otherwise, it's 0. The way we can write this is as the negative indicator, sort of one indicator, of I being equal to y. All right, what about this next term? What is the derivative with respect to hi of this term? Well, now we have to just sort of do it. So let's apply the basic chain rule. So the derivative of the log of something is the derivative of the thing inside divided by that thing, right? So this is going to be equal to plus the derivative of this thing, the thing inside the log. So that's going to be the derivative with respect to hi of the sum from j equals 1 to k of the exponential of hj, all divided by the sum from j equals, write it like this, j equals 1 to k of exponential of hj. But now, this numerator here, well, if I'm taking the derivative of the sum of all these exponentials, again, I'm taking a partial derivative with the hi of this sum. And because all the terms but hi are considered to be constants. In fact, here I'm actually, the reason why I use j there, by the way, in this case, was because I'm differentiating with the hi, not actually because of the examples. So this is just because I'm differentiating with the hi here. So I had to use the sum over j. But taking the derivative of this inside thing here, well, that's going to be 0 for all j except j equals I. And for that one j equals I term, well, the derivative of the exponential is just that same thing. So this whole thing here is going to be equal to the exponential of parentheses there, of hi divided by, see if I can write this without getting in the way of it, the sum from j equals 1 to k of exponential of hj. That'd be nicer. hj. But this thing here should look very familiar to you, right? It's just that same softmax operator we had before, right? It's the exponential of the hypothesis divided by the sum of the exponentials, i.e. the softmax, i.e. the normalization of the exponential of h. So we can write this whole thing much nicer, the whole derivative now much nicer in vector form. In particular, we can write this whole thing as the gradient of the cross-entropy loss with respect to h, which is equal to z, which is going to be here, z equals normalizing the exponential, that weirdly, exponential of h, or the softmax of h, minus a term that has minus this term here, which this term here is going to have a 0 everywhere except the 1 in the yth position. And a very common way of writing that is as z minus e sub y, where e is called the unit basis. Okay, so just to highlight everything in the end, this term here is our final gradient of the cross-entropy loss with respect to the input, its input, treating its input as a vector. Okay. So are we there yet? Like, so close, but so far, in a way. Because how do we compute what we really want? We actually don't want the gradient with respect to the input to the loss function. We want the gradient with respect to theta of this thing. How do we compute that? And it's I mean, the way you would do it, right, is you use something like the chain rule. Okay, because we want the gradient of with respect to something inside, you can use the chain rule. But the dimensions here are nasty. I mean, and this is like the simplest possible thing you can imagine, right? It's a linear hypothesis function, but this term here is a matrix. This term here is a vector, so we want like the derivative of a vector with respect to a matrix. It's like some odd tensor. It turns out this gets really cumbersome really quickly. And so we need some sort of more powerful or more kind of almost a rigorous, because what we're about to see on the slide sort of throws that out the window. But we need some sort of more general and generic way to take derivatives when we have multivariate, multidimensional matrix quantities, etc. Eventually tensor quantities, stuff like that. So how do we do this? Well, there's two things we can do. We can first do the right thing. And to be clear, the right thing is you can define generalizations of gradients like Jacobians that actually are the derivative of a vector output with respect to a vector, or the matrix of all partial derivatives there. But when you have then matrices you're differentiating with respect to, you need to use things like Kronecker products and vectorization. But you can formalize all of this using matrix differential calculus. So there really are ways to sort of go through formally what every single derivative you want to compute here, or every single sort of gradient and partial derivative and Jacobian here is. You can also do this out term by term, but that's even worse. But you can do this all very formally with matrix differential calculus. We're not going to do that, though. What we're going to do is the horrifying but thing that everyone actually does, which is the following. And if you haven't seen this before, this is going to be like a revelation to you if you've done these derivations before and never realized that what people actually do is this thing. So I'm like pulling the cover back here on, the big secret, but it's not even a useful secret because it's how we used to do these things. So this is how we used to do them, and now it's useless. But anyway, pulling back the big secret here. The thing you do to compute multivariate Jacobians, gradients, derivatives, whatever, is you just pretend everything's a scalar, apply the normal chain rule, and then rearrange or transpose your outputs such that everything works in terms of the sizes. And I really want to highlight this sort of horror emoji here. It is should be suitably horrified by this. Okay. So this is what actually is done in practice, and it is a bit horrifying, but this is what people really do. And it actually you get sort of used to it quickly. The thing I will say, though, is what's very important to do if you ever do this is to check your answer. And check your answer numerically. So we'll show actually in the next lectures how you go about checking derivatives numerically. You'll do it in the second homework. This is because so much can go wrong with this first approach. You can use it as a hack, but then check your answers after the fact. But this is literally what we do when we want to compute nasty gradients or nasty high-dimensional derivatives, whatever. Doesn't always work, but it works a surprisingly large amount of the time, and so always at least try this first. Okay, so how does this actually work? So let's say let's try to compute this quantity. Let's try to compute the derivative of the cross entropy loss of our hypothesis function. So this is the thing we actually want to compute the gradient of. But let's do it assuming everything is kind of a scalar. And I'm still going to use the partial derivative sign here, even though I should probably use like just the normal not scripty d's at this point. But I'm going to use the partial derivative sign to kind of to remind me that I'm horribly cheating here and should never actually do this. But let's just do it. Let's pretend all of this really is scalar valued and kind of go from there. All right, so what is this? Well, now we can apply the normal. So if we're computing this derivative, now we can apply kind of the normal chain rule. So the thing would be the derivative of the loss, the cross entropy loss of theta transpose x, and y with respect to theta transpose x, that argument to the cross entropy loss, times, and it doesn't matter what this what times means here because they're all scalars, so it just means scalar multiplied by the derivative of theta transpose x. And obviously we don't need transposes, they're all scalars now, but we'll still just include it because you can always transpose a scalar, that's fine. With respect to theta. Okay, so that's what we do. So what are those things? Well, now if they're all scalar, we actually can write this out really easily, right? So this first thing here, this first term, this is actually just the derivative of the cross entropy loss with respect to its argument. That's exactly what we had last time, right? So this is actually going to be equal to exactly what's on the 2 slides ago. It's going to be z minus ey, okay? Where here z, just like before, is equal to normalizing the exponential of, in this case, the hypothesis, which is going to be theta transpose y. Times, well, this one here, when they're all scalars, is really easy. The derivative of theta times x with the theta is just x. All right. Now we're almost done. All we have to do now is talk about what size these things are. All right, so this thing here, z and ey, those are both k-dimensional vectors. So this is a k-dimensional vector, really a k by 1 dimensional matrix. And this term here is x, so that's just going to be an n by 1 dimensional vector, or again, n-dimensional vector, and n by 1 dimensional matrix. All right, so how do we compute this gradient here? The gradient we want is n by k. So how do we arrange those two terms, this term and this term, to make an n by k dimensional output? Well, the way we would have to do it, and the only option we have, is to take this and say this is going to be x times z minus ey transpose. That makes an n by k dimensional matrix. And that, in fact, is the correct gradient that we are after. So yes, this is very embarrassing that we do it this way, but we do it this way. And in fact, even in some of the deriving some of the gradients for individual operations in automatic differentiation, you will also do it this way. Okay, so the funny thing about this is this even works for like the batch case too. So we can, again, kind of abusing notation a bit, we can write the loss function we really want for a whole mini batch, right? Which is sort of the loss function applied to the hypothesis of a whole mini batch, which is x times theta. We can write this all in the exact same way. So things actually are exactly the same as before. If I want the derivative of this with respect to theta, of loss, cross entropy loss of x, theta, and y, well, that just will equal the derivative, the partial derivative of the cross entropy loss of x theta and y. This is now matrices. It's the only difference from before. Partial derivative with respect to x times theta, and then derivative of x theta with respect to theta. Okay. This thing here would equal, well, I'll write it like big Z minus like I subscript y. What this is saying here is this is big Z here would be something like normalizing, taking the hypothesis, applying it to all the elements in our matrix X, and then normalizing by rows. So it would be like normalize, and I mean normalize here by row. I'm gonna run out of space, I'm running this myself, of x theta. Okay, that's what big Z is. And IY, that's like a one-hot encoding, like the EY in each row. So it's like a one-hot encoding of the output classes. But then times X as before. All right, so this, and now we just do the same exact thing. So this matrix here, kind of running out of space right below, but like this matrix here would be M by K, because we would have each row would be kind of these terms. And we already know that x here is m by k, right? So how do we get our final product, which again, our final product is still n by k? Well, what we do is we take things to transpose them properly. It would be x transpose, right? So x is m by k, so we want k by m, and then times this thing here, times z minus iy. And that, oops, let me actually just highlight it. This here is the actual gradient we want. So, like how many characters this is, 10 or so characters. That's the actual gradient we want. And now you might be sort of curious, why is this transpose, why are these transposes here kind of reversed from this one? Remember that our big matrix X here, we had the rows are already kind of the transpose versions of the individual entries. And so to compute this sort of properly, you have to transpose them depending on how you set up these matrices. But this thing here is the final expression we're after. And that's actually somewhat confusing. I mean, this is now a matrix. This is another matrix here. It's quite cumbersome to do this properly with Kronecker products and tensorization or vectorization, all that kind of stuff. But again, once you've derived it, you can in fact check numerically this is the correct thing, and it is in fact the correct gradient. So I just want to call you out to the title of this slide again. It is rather embarrassing that we do things this way. You will eventually not do this at all in this course, because of course this course is going to be about how you build automatic differentiation tools that let you avoid this. But this is how we used to do machine learning. This used to be the trick that everyone sort of did in machine learning, and maybe no one really talked about. But now you know the secret too, if you want to do kind of old style machine learning. One thing I will mention here before I go on, and we're pretty much done now, but the one thing I will mention here is that it's really easy to screw this up. So like these sizes are really important. So if you for example choose k equal to n, then it's really easy to mess up the dimensions here. So you have to choose the dimensions as different as possible, as you could be, to make this all work. All right, but now we are done. So despite what I admit is a fairly complex derivation, what we are left with for softmax regression is something incredibly simple. And I really want to emphasize this simplicity. Okay, what does the final softmax regression algorithm look like? Well, you split up your data, your training set, into batches. You iterate over these batches of size b. So you iterate over your training batches of size b. And for each batch, you just update the parameters according to this gradient rule. I guess there's sort of one, I mean, obviously you have to compute what z is to really do this, but this is 5-6 lines of Python code. All those derivations you saw ultimately translate to an incredibly straightforward, simple algorithm to implement, which you will actually implement on the first homework. And that is the entirety of the softmax regression algorithm. So despite, some non-trivial math to get there, and you should be acknowledge the fact that this is not completely trivial, these derivations here, even though we kind of cheated our way into the hard part of the derivation. This is ultimately kind of a one-line description of the actual resulting algorithm, which you can implement, again, in a few lines of Python code. And if you do it and implement this on the MNIST data, you'll find you get about a little bit less than 8% error. So that is probably better. Again, 10-way classification, one of 10 classes. With a linear hypothesis class, you're able to get 8% error. That is probably better, maybe, I'm not quite sure, but that's probably better than what I could do by hand. So that's really, really impressive. And what we're going to do next lecture is we're going to do the same thing, basically in the exact same way. The only difference is we're going to use neural networks. But what that means is just a fancier hypothesis class. We're going to use the same basic loss function, the cross-entropy loss. We're going to use the same optimization procedure, gradient descent or stochastic gradient descent. Naturally, computing the gradients is a bit trickier, but the procedure is the same. And the only difference for deep learning in some sense, or for neural networks, is that we use a fancier nonlinear hypothesis class instead of the linear hypothesis class of softmax regression. That's going to be next time. And for one more lecture next time, we are going to go through this the old tedious way. And after that, we'll go through it the nice way, where you can now, after next lecture, I guess after you've implemented automatic differentiation 2, you can forget about gradients and let the automatic differentiation tool that you write actually do all this math for you in the proper way, I should mention too. All right, see you next time.